Learning outcomes. After studying this module, you shall be able to know about methods of the naming of chiral molecules, learn various methods to denote the absolute configuration of optical isomers, identify DL system, RS system for naming the complexes, identify delta and lambda notation for the naming of complexes, allocate stereochemical notation to the given optically active complex. Introduction. In this module, we will discuss about the stereochemical notations in coordination complexes, that is absolute configuration of complexes. Various systems we can use for the coordination complexes are DL system. This is actually the simplest method in which we use the direction of the rotation of plane polarized light. Isomer or the enantiomer that rotates the plane of polarization to the right is said to be dextrorotatory, and the enantiomer which rotates the plane of polarization to the left is said to be levorotatory. But this notation for the configuration of complexes is very simple. So we can also use RS system. RS system are used to describe the absolute configuration of disymmetric complexes according to Kahn-Ingold-Prelog system, and this system is commonly used in organic chemistry. The IUPAC rules suggest that the general octahedral complexes CA scheme is convenient to use. CA scheme was only for the complexes having monodentate ligands, but for the complexes having bidentate or tridentate ligand, we can use the notation that is capital lambda or capital delta notation. This is notation for the disymmetric complexes of bis and tris bidentate ligand. The absolute configuration can be described using capital lambda and capital delta notation. Capital delta is used when chelate ring described right-handed helix. However, lambda is used when they describe left-handed helix. However, there is another notation, that is small lambda and small delta notation. This is used to describe the conformation of individual chelate rings. Delta describes a ring of right-handed helicity. However, lambda denotes a ring of left-handed helicity. And in this module, we also discuss some questions based on these naming systems. Stereochemical notation in the coordination chemistry. Absolute configuration of the complexes. There are several different ways to represent an octahedrally coordinated metal ion shown here. Which way we choose depends on the method for naming the chiral complex. Although the naming of the chiral molecules is a tedious job, but various methods have been proposed to denote the absolute configuration of optical isomers. These are DL system, RS system, lambda and delta notation, small lambda and delta system. Let us now briefly discuss the meaning of denoting such configurations. First is DL system. The simplest method is the notation on the basis of the direction of the rotation of plane polarized light. The isomer that rotates the plane of polarization to the right is said to be dextrorotatory. It is labeled as dextro or D isomer or plus isomer. Its mirror image rotates the plane of polarization to the left, and it is said to be levorotatory and is labeled as the levo or L isomer. Normally, in the case of coordination complexes, plus lambda or minus lambda are used to designate the sign of rotation of plane polarized light at the specified wavelength lambda. When the sign appears without the wavelength noted, the wavelength is assumed to be that of a sodium D line, which is 589 and 589.6 nanometer. For example, plus subscript 589 cobalt ethylene, it is dextrorotatory with respect of light of sodium D line. This method of naming of complexes is not found to be appropriate because when optical activity of the tris 1,2-diaminomethane M3 complexes, M can be rhodium 3 and cobalt 3 was measured at the sodium D line, means 589 nanometer. They rotate the plane polarized light in opposite directions. However, they are having the identical absolute configuration. So, we choose another way of naming the complexes, and that is RS system. RS system are used to describe the absolute configuration of disymmetric complexes according to Kahn-Ingold Prelog system, CIP system. This system is commonly used in organic chemistry. The IUPAC rules suggest that for general octahedral complexes, CA scheme is convenient to use. CA scheme works only for the complexes having monodentate ligands. For the coordination complexes, also the priorities are assigned for mononuclear coordination systems based on the standard sequence rules developed for enantiomeric carbon compounds by Kahn-Ingold and Prelog rules. These rules use the coordinating atom to arrange the ligands into a priority order such that the highest atomic number gives the highest priority number, smallest CIP number. For example, the hypothetical complex chromium 3 chloride bromide amino nitro SCN would assign the priorities to the group iodide as 1, bromide as 2, chloride as 3, thiocyanate as 4, nitro group as 5 and amino group as 6. Here is one isomer where the ligand iodide and chloride and bromide and nitro were found to be trans to each other. The reference axis for an octahedral center is that axis containing the group of CYP priority 1 and trans-ligating atom of lowest possible priority or highest numerical value. The atoms in the coordination plane perpendicular to the reference axis are viewed from the ligand having the highest priority, and the clockwise and anti-clockwise sequences of priority numbers are compared. The structure is assigned the symbol C or A according to whether the clockwise or anti-clockwise sequence is lower at the first point of difference. The reference axis for the complex shown here will be containing iodide and chloride ligands. According to the rules, rotation is clockwise, thus the structure is assigned the symbol C. Another isomer of the same complex is shown here. For this complex, the ligand iodide and bromide and chloride nitro were found to be trans to each other. The reference axis for this complex will be axis containing iodide and bromide ligands. According to the rules, rotation is anti-clockwise, thus the structure is assigned to be of symbol A. The two optical isomers of this complex have identical chemical properties, and just denoting their absolute configuration doesn't give any information regarding the direction in which they rotate plane polarized light. This can only be determined from the measurement, and then the isomers are further distinguished by using the prefixes plus and minus depending on whether they rotate left or right. For tetrahedral complexes, R and S would be used in a similar method to tetrahedral carbon species and although it is predicted that tetrahedral complexes with 4 different ligands should be able to give rise to optical isomers. In general, they are too labile and cannot be isolated. Another way of representation is capital lambda and delta notation. For disymmetric complexes of bis and tris bidentate ligands, the absolute configuration can be described using lambda and delta notations. Lambda is used when chelate ring describe right-handed helix. However, lambda is used when they describe left-handed helix. The handedness can be understood by taking the example of propellers. These propellers are enantiomers of each other and they can describe a left-handed and a right-handed helix on rotating and moving through space. If we fix our eye on one blade, that point will describe a helix as the propeller rotates while moving through the space. The two propellers here are different in their direction of rotation. First propeller describes a left-handed helix, however, second propeller is a right-handed helix on moving through the space. A tris bidentate metal complex can trace out a left-handed or a right-handed helix on rotating and moving through space exactly in the same way a propeller have helices. Procedure for determining handedness. First, we rotate the figure to place one ring horizontally across the back at the top of one of the triangular faces. Then imagine the ring in the front triangular face as having originally been parallel to the ring at the back. Determining what rotation is required to obtain the actual configuration. If the rotation from step 2 is counterclockwise, the structure is designated lambda. If the rotation is clockwise, then designation is delta. Here we illustrate another way of determining handedness is to look directly at the triangular face of an octahedron. The 3 nitrogen atoms shown on the upper triangular face of the octahedron are chosen to represent one of the binding site in each of the 3 ligands. However, each of the nitrogen atoms on the opposite or the lower triangular face are connected to one of those on the upper face with an arc representing the ligand backbone. The right-handed or delta isomer requires the movement of backbone from the upper triangle to the lower one in clockwise direction. On the other hand, the left-handed isomers requires going counterclockwise to get from the upper triangle to the lower one, and the prefix for the isomer is delta. Another example is tris oxalato cobalt complex. In the left isomer, the movement of backbone from the upper triangle to the lower one is in clockwise direction. So this isomer is right-handed isomer and the prefix for this isomer is delta. However, for the isomer on the right side of the figure, the movement of backbone from the upper triangle to the lower one is in counterclockwise direction. So this isomer is left-handed isomer and the prefix for this isomer is delta. Another naming for the complexes is small lambda and small delta system. Notation: lambda and delta are used to describe the conformations of individual chelate rings. Delta denotes a ring of right-handed helicity and lambda denotes a ring of left-handed helicity. When a bidentate ligand is bonded to a metal ion, 5-membered or 6-membered chelate ring depends on the number of atoms in the ligand backbone. Although the two donor atoms and the metal must be in the same plane, backbone atoms are not coplanar with them and the two conformations are possible for the ligand. This is shown here with the ligand ethylene diamine. Delta and lambda system is available to designate the twisting of the backbone atoms in chelate ring, and this is relative to the N plane of atoms. Consider the ligand bonded to the metal as shown here. If all 5 atoms involved are imagined to be in a single plane, this is called a gauge conformation. Although not met in practice, gauge is the starting point for analyzing actual conformations. Relative to all atoms in a same plane, note how the backbone would need to rotate in order to adopt each conformation shown here. On the left, backbone atoms would be rotated in a clockwise direction. On the right, backbone atoms would be rotated in a counterclockwise manner. The symbols used are lowercase Greek letters delta and lambda respectively. The conformation of one ligand is independent of the other. For a tris bidentate complex having the absolute configuration delta and 3 ligand chain with conformation lambda, lambda and delta, the designation for the complex is written as delta, small lambda, small delta. This informs that and 2 of the rings have lambda conformations while the third has delta conformation. For example, tris ethylene diamine cobalt 3 complex is shown here. Absolute configuration of the complex is delta. Compare the figure at the right. The conformation of 3 bidentate ligands are delta, lambda, lambda as labeled here. Study questions. Question 1. Assign the lambda and delta chirality label for the complexes cis dichlorobis ethylene diamine cobalt 3 complex. For first one, rotate the figure 180 degree above the vertical axis in such a way that one ring comes across the back and other connecting the top and the front right positions. If this front ring was originally parallel to the back one, a clockwise rotation would put into the correct position. Therefore, the structure is delta. Thus, the name of this complex would be delta cis dichlorobis ethylene diamine cobalt 3. For the second one, rotate the figure at 90 degree about the vertical axis in such a way that one ring comes across the back and the other connecting the top and the front right positions. If this front ring was originally parallel to the back one, a counterclockwise rotation would put it into the correct position. Therefore, the structure is lambda. Thus, the name of this complex would be lambda cis dichlorobis ethylene diamine cobalt 3. Alternate method for solving question number 1, part 1 is to rotate the figure 180 degree about the vertical axis in such a way that one ring comes across the back and other connecting the top and the front right positions. Now draw the upper and lower a triangular face of an octahedron. The 2 nitrogen atoms shown on the upper triangular face of an octahedron are chosen to represent one of the binding sites in each of the 2 ligands. However, each of the nitrogen atoms on the opposite or the lower triangular face are connected to one of those on the upper face with an arc representing the ligand backbone. The movement of backbone from the upper triangle to the lower one is in clockwise direction, means right-handed or delta isomer. Thus, the name of this complex would be delta cis dichlorobis ethylene diamine cobalt 3 complex. Alternate method for solving question number 1, part 2nd. Rotate the figure 90 degree about the vertical axis in such a way that one ring comes across the back and other connecting the top and the front right positions. Now draw the upper and the lower triangular face of an octahedron. The two nitrogen atoms shown on the upper triangular face of the octahedron are chosen to represent one of the binding sites in each of the two ligands. However, each of the nitrogen atoms on the opposite or the lower triangular face are connected to one of those on the upper face with an arc representing the ligand backbone. The movement of backbone from the upper triangle to the lower one is in counterclockwise direction, means left-handed or lambda isomer. Thus, the name of this complex would be lambda cis dichlorobis ethylene diamine cobalt 3 complex. Question number 2. Assign chirality label delta or lambda for the conformations of the chelate ring for the chiral structures of the complex trans dichloro triene chromium 3, trans chromium triene chloro 2 shown here, where triene refers to triethylene tetraamine, which is tetradentate ligand, and form 3 chelate ring around the metal center. Solution for this question. The structure of the triethylene tetraamine is shown here, and also the 4 binding site of the ligand are shown with the help of blue arrows. The conformation of 3 ethylene rings are established by using same method discussed under previous section. Summary. In this module, we discussed various methods to denote the absolute configuration of enantiomers. These methods are DL system, RS system, capital delta and capital lambda notation, small delta and small lambda notation. DL system is based on the rotation of plane polarized light by the enantiomer, whereas RS system is based on the priority of the groups attached to the central metal ion. Capital lambda and capital delta notation is based on the left-handed or right-handedness of the helix, ligand helix attached to the metal center. However, small delta and small lambda system is based on the rotation of the ligand system attached to the metal center.